Welcome, my dear students. We are going to study nuclear spin. Nuclear magnetic resonance (NMR) measures the magnetic effects of a nucleus caused by spin of protons and neutrons with the help of radio frequency radiation. Nuclear magnetic resonance spectroscopy involves the change of the spin state of a nuclear magnetic moment when the nucleus absorbs electromagnetic radiation in a strong magnetic field. The spin possessed by the particles is responsible for the angular momentum and the magnetic moment, means the spin angular momentum and nuclear magnetic moment. Certain nuclei, when kept in a magnetic field, the energies of the nuclei were split up into two or more energy levels, which are quantized. When this is exposed to appropriate radio frequency radiation, or the nucleus absorbs the energy by resonance, and the transition takes place from one energy level to another. This phenomena is known as nuclear magnetic resonance. Nuclear spin. The nucleus contains protons and neutrons together called nucleons. They possess a spin known as intrinsic spin. The spin of the nucleus is therefore considered as resultant of the spins of the protons and neutrons present in it. As a result of intrinsic spin, some nuclei possesses a spin angular momentum which depend upon the resultant nuclear spin quantum number I. The spin quantum number is the vector addition of protons and neutrons spin number of half each. The resultant spin angular momentum of the nucleus is given by the expression: the spin angular momentum is equal to square root of I in bracket I plus 1 into bracket separate into h upon 2 pi, where h is a Planck's constant. The nucleus is positively charged. Though all nuclei are positive charged, only some of them possesses a spinning property. The spin characteristics of nuclei are defined by a spin quantum number I, capital I, which gives rise to a spin angular momentum. The magnitude of the spin angular momentum is related to the spin quantum number I. All fermions, that is a proton, neutrons, electrons, possesses spin. All fermions possesses half integral spin. The spin of the particle is responsible for its spin angular momentum, its magnetic moment, and its interaction with the magnetic field. The vector sum of the proton and neutron is a half integral spin can be 0. Half integral or integral depending upon whether the protons and neutrons in the nucleus are paired or unpaired. The magnitude of the resultant spin depends upon whether the protons and neutrons are odd or even in number. Rule first: if the nucleus contains even number of protons and even number of neutrons, then the total spin of the nucleus is 0. They have even charge and mass. They have 0 spin. For example, twice He4, 6 carbon 12, 8 oxygen 16, 16 sulfur 32, 20 calcium 40, 12 magnesium 24, 14 silicon 28. Here if you consider the helium, twice He4, 2 protons and 2 neutrons, means even number of protons and even number of neutrons. These molecules cannot be studied in the NMR spectroscopy. Even number of protons and even number of neutrons, then these molecules cannot be studied in NMR spectroscopy. Rule second: if the nucleus contains both odd number of protons and odd number of neutrons, the total spin of the nucleus is integral. For example, 1H2, thrice lithium 6, 5 boron 10, 7 nitrogen 14. The spin number of 1s1, 5 boron 10, 3, 7 nitrogen 14 1. only 4 nuclei exist. These exhibits odd number of protons and odd number of neutrons, and the total spin of the nucleus is a integral. Rule number 3. Nuclei with either odd number of protons or neutrons will have integral spin. Odd number of protons or odd number of neutrons, but not both odd, they have half integral spin number. For example, 1H1, 6 carbon 13, 5 boron 11, 7 nitrogen 15, 15 phosphorus 31, 9 fluorine 19. Spin number for hydrogen half, carbon half, 5 boron 11, 3 by 2, 7 nitrogen 15 half, 15 phosphorus 31 half, 9 fluorine 19 half. Means the spin number for the boron is 5 boron 11 is 3 by 2, but for hydrogen, carbon, nitrogen, phosphorus, fluorine, it has half spin number. The proton hydrogen atom nucleus spin about its own axis. The positively charged spinning proton generates a small magnetic moment, making the proton behave like a tiny magnet. It is the nucleus that contains the protons. As a result, the nucleus also possesses spin. The spinning nucleus generates a magnetic moment. The spin of the nucleus is the vector sum of the spins of the protons and neutrons present in the nucleus. Now, depending upon the resultant spin of the nucleus, it may or may not behave as a magnet. In order to obtain nuclear magnetic resonance spectra, a nucleus must possess a spin. Such nuclei are called spin-active nuclei. Nuclei with zero nuclear spin do not give NMR spectra. Nuclei with zero nuclear spin do not give NMR spectra. Nuclei with integral or half integral spin will possesses a spin angular momentum, means non-zero spin, then it possesses spin angular momentum, magnetic moment, and will interact with the applied magnetic field and will behave as magnet, and it will be responsible for the nuclear magnetism. Nuclei with zero spin will possess a zero angular momentum, zero magnetic moment, and hence will not be able to interact with the applied magnetic field. The behavior is similar to diamagnetic behavior of atoms, molecules, or ions with all electrons pair. All electrons are pair. All electron pair, there is a diamagnetic behavior. Paired electrons, then diamagnetic, unpaired electrons, paramagnetic. The magnetic moment of a nucleus is a result of its spin and the angular momentum due to spin angular momentum of the nucleus. Therefore, basic unit of the magnetic moment of the nucleus, mu, should be in terms of the basic unit of angular momentum, spin angular momentum. Basic unit of magnetic moment has to be defined in terms of the spin angular momentum of a single nucleon. Hence, basic unit of nuclear magnetic moment, beta n, that is the nuclear magneton, is defined as beta n is equal to in bracket E divided by mp, then into h upon 2 pi. It is expressed in Tesla T units. The E is a charge on the proton, then the mp is the mass of the proton, and Bn is the unit of nuclear magnetic moment, that is the nuclear magneton. Here there is a nuclear magneton for the, if you consider the mass of a proton, and if you consider the electron, then there is a Bohr magneton. Similarly, the basic unit of atomic magnetic moment, Bohr magneton, can be defined as Bohr magneton is equal to E upon me into h upon 2 pi into half, where me is the mass of the electron. If you consider the beta n, that is the nuclear magneton, then the Bohr magneton is for the electron, nuclear magneton for the proton. Thank you.